Alright, welcome back. In this video, we're going to be talking about transformations of functions. And this is a topic I've kind of saved till the end until we had our feet under us algebraically and a good knowledge of a library of parent functions. And now that we know all sorts of functions like polynomial, radical, rational, exponential, logarithmic, we're going to kind of move them around a little bit. So what we're doing is we're hitting a few different teaks here where we're determining the effect on the graph of y equals f of x when f of x is replaced by a times f of x adding d after the fact, f of b times x, and f of x minus c for specific positive and negative values of a, b, c, and d. Okay, so we're going to start by considering the function f of x equals x squared. We know how to graph this. I'm going to just draw it in right now. Okay, but I might ask you to graph f of x minus 2, but I just need to remind you of a few things first. First would be the vertex form of parabola. A long time ago in this class, we took a quadratic and we could write it a times x minus some x coordinate squared plus some y coordinate. We knew that the vertex of that parabola was going to be at x0, y0. And then more recently, we learned about what to do when we were confronted with something like f of x minus 2. Okay, so if we've got f of x and that's x squared, f of x minus 2, wherever I see x in the formula for f, I'm going to replace it with x minus 2. So I'm going to say f of x minus 2. I'm taking whatever I'm putting into f and I'm squaring it. So it's going to be x minus 2 squared. Okay, so x minus 2 squared with nothing added to the outside is going to be a parabola that has a vertex at 2, 0. So I'm going to put the vertex there. And then we could plot another couple of points. We could plug in x equals 0 in here, and we'd see that y would be negative 2 squared is positive 4. And then you can see it's just otherwise going to be the same type of parabola because it's got that leading coefficient of 1 right there. But I think that that'll probably be enough for you to see that this has just been the same parabola shifted to the right by 2 units. And if I wanted to write f of x minus 2 as a composition of functions, I would say, all right, well, I've already got f of x equals x squared, and what I did was I plugged something new into f, right, x minus 2. So I'm going to say this is going to be f of g of x, where f of x equals x squared, and g of x equals x minus 2. And I'm going to keep doing this for each of these types of transforms. I'm going somewhere with this, but I really need you to be able to, look at something abstract and write as the composition of functions. Before we move on, I want you to consider what would have happened to the graph of y equals x squared if we had considered f of x plus 3 instead of f of x minus 2. Okay. What would have happened is it would have moved the vertex to negative 3, 0, and so it would have effectively shifted the graph left 3 units. So to kind of wrap up the horizontal translation situation, we could say if we wanted to shift the graph of f left by a units, we would replace f of x with f of x plus a. If we wanted to shift the graph of f right by 8 units, we would replace f of x with f of x minus a. All right, next, I might like to talk about a horizontal stretch. Okay, so we moved it left and right. What if we wanted to stretch it horizontally? So we're going to start with the graph of y equals absolute value x, which you might remember looks like a v. But if we wanted to graph f of 1/2 x, we could just replace x with 1/2 x. So I could say f of 1/2 x would be the absolute value of 1/2 x. And you might remember from when we did that if we manipulated the x on the inside, that really just changed the slopes of the two lines. Okay, so it would just be a slope of a half and negative a half. So I'd be seeing this kind of situation here. And then over here, probably don't want to see me trying to draw this. Struggle going right to left with this machine. Okay, and then we might also be interested in graphing f of 3x. And I could say that's okay, f of 3x is going to be the absolute value of 3x, which would make the slopes 3 instead of 1. Okay, so if the slopes were 3, I'd be going over here. And let's see, coming up like that, and over there. And let me kind of, ooh, wow, that was rough. Let me just kind of label these. So what I'm trying to get you to see here is that replacing x with half of x on the inside, that actually serves to make a stretch. Okay, now you probably wouldn't think that. You would expect that f of 3x would make it 3 times as wide, but it actually works the opposite of the way we expect. Kind of like how subtracting on the inside ended up shifting our graph right. Okay, so there's something about that, where it works the opposite of what we expect, but I'd say that, that might be a discussion better saved for pre-cal. For now, I'd say let's look at the evidence and draw our conclusions based on what we can see based on the graphs we're sketching. So f of 3x made it 3 times as narrow, whereas f of half x made it twice as wide. Now I'm just going to do the same thing. If I wanted to write f of 3x as a composition of two functions, again, what happened was I took 3x and I plugged it into f. So this is going to be an f of g of x, where f of x is what we were already working with, absolute value x, and g of x is equal to 3x. Okay, notice it's going on the inside again. Okay, so to kind of wrap up the thing about horizontal stretching, we could say that a horizontal stretch would happen if we had, kind of like a proper fraction multiplied by x on the inside, so like 1 over b times x. If we were trying to horizontally stretch by a factor of like a, we'd do 1/8 of x. If we were trying to horizontally compress by a factor of, say, 7, I would multiply x by 7 on the inside. Okay. Let's move on. I think we've got another horizontal transform. Yes, horizontal reflection. So let's remind ourselves about the function f of x equals natural log x. Let me just draw you the graph real quick. No, wait, I was going to remind you what the shape of the graph looked like by finding the value of f of 1. Okay, so f of 1, that's equal to natural log of 1, because f of x is natural log of x. Okay, so, and when I'm taking natural log of 1, what I'm asking myself is what exponent do I put on e to get 1? And it's got to be something pretty obvious. It's going to be e to the 0 equals 1. So we're going to say f of 1 is the natural log of 1, which is 0. So I've got the point 1, 0 on my graph. Okay, and then I'm going to remind you that it's the natural log of x is the exponent I put on e to get x. And so, to get a bigger value of e to the x, I have to put on a bigger exponent, but exponential functions grow really fast. And so that's what the graph looks like. And we studied log functions not too long ago, so this shouldn't be too unfamiliar. Okay, so we've graphed f of x. And I think what would be important to remind you about f of x is that the domain of this thing was we took the inside of the function and we set it greater than 0. Okay. And I'll be interested in that when I go to talk about f of negative x. So let me go over here, I'll switch up the color a little bit, and say, all right, f of negative x, negative x, is going to be equal to natural log of negative x. And if I wanted to find the domain of this thing, I would be grabbing the inside of the natural log, and I'd be setting that greater than 0. So we'd be saying, all right, negative x is greater than 0, and that happens to be when x is less than 0. Okay, so I'm having the exact opposite domain. And moreover, okay, if I think about what would I plug in here for x in order to be taking the natural log of 1, the 1 point I already know how to do, I'd be plugging in negative 1, right? And here, because f of negative 1 is going to be natural log of 1, that would be 0. Okay, so over here I've got negative 1, 0, and then if I think about, okay, this act of putting in an x into f of negative x, or log of negative x, what's going to happen is all of these negative numbers, they're going to become positive. So that's why we're seeing the reflected version of the same graph. It's because all of the action that had happened when x was positive is now happening where x is negative, and we see a reflection in the graph, or at least we're supposed to. So just to summarize, replacing x with negative x causes a reflection across the y-axis. And to do the same thing I did on the other two types of transforms, I'm going to write f of negative x as a composition of two functions. So this is going to be f of g of x, where f of x is that natural log function we were working with, and g of x is negative x. Hey, and what I was getting at this whole time is that horizontal transforms, all of these transforms we've been looking at, they can always be viewed as a composition of functions on the inside of the parent function. And that's something that they would, tell you to remember in a standard algebra class. Transforms on horizontal transforms affect the inside of the parent function, whereas vertical transforms are going to impact the outside. But let's look at that now. Now, I think the vertical transforms are actually a little easier to understand, and, well, for that reason, I've been kind of slipping them in here and there throughout the course, and so they might seem a little more familiar too. So let's start with y equals x cubed. We're going to sketch the graph of f of x. We studied this curve a couple of times in this class. It looks in some ways like a parabola, but it doesn't open both sides up. Okay, we've got one side going up, one side going down. So that's the graph of y equals f of x. F of x plus 1 would be, okay, well, y equals f of x plus 1. I'm going to just take this really literally, and wherever I see f of x, I'm going to replace it with x cubed. Well, that's just y equals x cubed plus 1, and we know how to graph that. Okay, all of the y coordinates are just 1 higher than they would have been otherwise. So that will just shift the graph up by 1. We can do that. I always struggle with drawing this. I mean, probably should have just chosen a different type of graph that I could make look a little better. I think it has to do something with the curvature. I mean, I copy pasted those curves to make sure that I could get them like kind of parallel to one another, but it's all right, no big deal. Now what we're supposed to see here is that the graph of f shifted up by 1 unit. Now, if I wanted to write f of x plus 1 as a composition of two functions, I would say that this was g of f of x, right? Because what I was doing was really, I could look at this as plugging f of x in for x in some kind of expression where, okay, f is what I'm used to. F of x equals x to the third, and g of something just takes that thing and adds 1 to it. Okay, so g of x is going to equal x plus 1. And so our vertical shifts would be, okay, if I'm going up by d units, I just take a f of x and I add d on the outside. If I want to go down by d units, I'm going to take f of x and I'm going to subtract d on the outside. But I think that's something that we've already known about in this class. Vertical stretch is something I feel like we also have known about in this class. I've kind of used it pretty freely, just on a common sense level. But let's just think about it as if we don't already know. Let's think about f of x equals square root x. We've graphed that in this class. It makes kind of a sideways parabola, or at least part of one. There'll be more discussion on why that's the case in the next video. So we've graphed f of x. Now we might be interested in graphing 2 times f of x. But maybe first I'll start by writing 2f of x. Y would equal 2 times f of x, which is going to be the square root of x. Okay, that's 2 square root x. And okay, I think we did a little bit of this. We just said it was twice as tall. That's all we're talking about now, is that the graph is twice as tall. But we could just kind of make a table of values. Think about plugging in x equals 1. What's going to happen there? I'm going to have 2 times the square root of 1. That's 2 times 1. That's 2. I didn't even think about what happens if I plug in x equals 0. 2 times the square root of 0. That's 2 times 0. That's still 0. And then, if I plug in 4, that's the next number I know how to take the square root of. I'd have 2 times 2, and that would be 4. So what I would see is that this graph would be, kind of like we've said already in this class, twice as tall. And then if I wanted to write 2 times f of x as a composition of two functions, kind of like I did last time, looking at it as something that happened to f of x on the outside. So I'm going to say that this is g of f of x, where f of x is square root x. And g of x is just a function that doubles the input, so it's going to be 2x. Okay, but again, this vertical transform is something we're going to see on the outside of the function. So in conclusion, for a vertical dilation, right, whether we're stretching or compressing, whether it's getting bigger or smaller, if it's stretching by a factor of a, we're just going to have a times f of x. Okay, and if a was a number that was like smaller than 1, say a third, we were vertically compressing and making it a third as tall as it was, we would multiply by a third on the outside. This works exactly like we expect. Now the last kind of class of transformation I've got for you to look at today is going to be a vertical reflection. So we're going to talk about an exponential function. We've looked at these things in this class also. Okay, and this was the thing that, it grew. And exponential functions, they grow. They grow really fast. And they have a horizontal asymptote too. So we graphed y equals f of x. Negative f of x is a thing we graphed actually pretty frequently in this class. So negative f of x would be the negative of e to the x. Okay, and that's just y equals negative e to the x. And we call that like negative growth, I think. Really kind of for lack of better terminology, but okay, really just all of the y values became negative. And I like this one as an example because, at the beginning, or for f of x, the curve in black, all of the y coordinates are positive. But if I take y equals negative f of x, or if I take y equals negative e to the x, we know e to the x is always a positive number. Negative e to the x will always be a negative number. So we can see that taking a function and multiplying it by -1 on the outside, that's going to serve to reflect the function across the x-axis. And if we wanted to write negative f of x as a composition of two functions, we would say that that was g of f of x, where f of x was e to the x, and g of x was a function that took a thing and made it negative, so negative x. I think what I was trying to get you to see here was that, vertical transforms can be written as a composition of functions on the outside of the parent function. Comparable to horizontal transforms, which could be written as a composition of functions on the inside of the parent function. And just to remind you, a vertical reflection is where we're going to take negative f of x. So we can just kind of fill out all of our transforms. All right, now the last thing I want you to consider is the function f of x equals cube root x. And I don't even know that I want to graph this at all. I'm not going to. I'm not going to graph these things. I'm just going to write a formula for f of 8x. So if I look at what f really does, it takes a number and it takes the cube root of it. So if I plug in 8x here, I'm plugging in 8x into the cube root into the cube root, really. Okay, and one thing that we learned when we were studying radicals is that when we had a product in the radical, we could split it as the product of two radicals. So cube root of 8 times the cube root of x. So I could also say that this is 2 times the cube root of x, because the cube root of 8 is 2. And what I'm saying here is that we could describe this either as a horizontal compression by a factor of 8, which is what you would probably see if you just said f of 8x. Okay, we just learned about it, but if you go look it up, that would be a horizontal compression by a factor of 8, or stretch by 1/8. I never really know how to describe that. But you could also look at this as instead maybe something like 2 times f of x. So this could be a vertical stretch by a factor of 2. And I guess what I'm really trying to say here is that oftentimes there's more than one way you can describe these things, and it's kind of inherently confusing. So really, I'm going to try to ask you very direct, specific questions to limit the amount of confusion. And since you watched with me this far, I figured we could make a little reference table of our transforms. And I'm realizing I forgot the reflections, but I think that maybe you could look at the reflections as kind of stretches. Okay, but let me fill those in. All right, there you go. So I think really what I guess I would point out to leave you with is that, these horizontal transforms, they're happening on the inside of a function. We can look at them as a composition of two functions where they're really the actions happening on the inside, and vertical ones, the actions happening on the outside. So that's all I got for you for this video. Thanks for watching.